Hi there, I'm Jasminder Sidhu and I work at the University of Strathclyde with Daniel Oy. And today I'll be giving a quick overview of some of our recent work on finite key effects in satellite quantum key distribution. I'll start with first with a quick introduction and overview into why we want to consider satellite-based quantum communications. I'll then move on to the main part of our talk, which is modeling general satellite QKD systems and seeing what sort of implications it has on the system design, which will be beneficial for upcoming missions. Here we will motivate why finite block sizes are really important before introducing SatQma, which is our optimized finite key length software, which we've recently made available on GitHub. We'll then go through some applications where we'll use our optimized software to see what sort of insights we can get that might guide experimental efforts in these upcoming missions. So this will consider stuff like the system performance, expected annual secret key length generation, and comparing different protocols. We'll then wrap up with a quick summary of our work. So a lot of the contents of the talk today is on archive. You can see a lot more detail, which is work that I've done with my colleagues at Strathclyde, which are Tom, Duncan, Roberto, and Daniel. So as an introduction and overview, what we want to realize is a global networked infrastructure of quantum technologies. So the current barrier to that, unfortunately, is the direct transmission of quantum resources over a network. So specifically, the maximum number of secret bits that can be distributed over a lossy channel is upper bounded by its transmissivity. Now, this limitation can be overcome by using quantum repeaters and multi-hop quantum networks, where essentially you segment the total transmission line into smaller links, and using a series of Bell state measurements, you can teleport quantum entanglement from one node to another. However, quantum repeaters have their limitations. Specifically, each segmented link still is subjected to the same exponential losses. And at the moment, quantum repeaters are not to the experimental level that are required for global networking. Also, some regions are inaccessible. You wouldn't be able to place quantum repeaters in places that are geographically inaccessible. So this motivates why we want satellites. Specifically, it overcomes this direct transmission limit. It reduces the demand on the number of quantum repeaters that are required, and it reduces significantly the amount of noise in the transmission link. So on the bottom right, we show the link efficiency versus distance, which was published in Mrs.'s Nature paper in 2017. And this plot compares the link efficiency in a transmission line over an optical fiber and satellite to ground link. And what you can see is at a distance of about 1,200 kilometers, you get a very big order of magnitude difference. So this is a principal advantage of using satellites. So satellites help extend quantum networks, and this will typically involve using a configuration of both uplink, downlink, inter-satellite links. And through this, then you should be able to efficiently route entanglement from one node to another, as this short animation illustrates. And with that, what you would be able to then realize is distributed quantum technologies, which is one of the requirements for an application of quantum internet. So in terms of modeling SatQKD systems, we start first with a series of definitions that help us generalize our approach to model different SatQKD systems. And the first definition is what we call the system link efficiency. So this is the general electro-optical efficiency of our system, and it characterizes the performance of SatQKD. And we define the system link efficiency to be the satellite ODS link efficiency at zenith. So that is when the satellite reaches its max elevation in its trajectory. We use empirical data that was published in 2020 by Misius to construct a representative link efficiency versus distance or elevation curve. So what we have is a baseline of 27 dB at a time of 0, which we define to be when the satellite is at its highest elevation point. And then moving away from that, you get an increased link efficiency, so higher dB loss. Now we consider a baseline of 27 dB, which corresponds to MISIS's improved system at Dillinger, which has a receiver aperture of 1.2 meters. And what we can do is we can model different systems. So for example, a 40 dB system, which would correspond to a receiver aperture instead of 21 centimeters, by linearly scaling the link efficiency, so effectively shifting up or down the blue curve. We also categorize the losses in terms of two key categorizations. So the first of those that we'll consider is source losses, which we'll call the intrinsic quantum bit error rate. So this will include non-ideal signals, satellite OGS misalignment, and imperfect projecting measurements. So these losses will be independent of our count rate and the channel loss. The second categorization of losses that we'll consider are the extraneous count probabilities, or PEC for short. And this includes the dark count rate, background light, and this is elevation independent. So with all the losses, we complement these two categorizations, and we will revisit how the key length varies with these two parameters later in the talk. Looking at the general overpass geometry of a satellite allows us to introduce a few more definitions that will be useful. So when the satellite reaches its highest elevation in its trajectory, theta max, it projects a distance of d min from the OGS, which we call the ground track offset, which is shown in green. Now, as the satellite continues in its overpass, it reaches a specific elevation after which the secret key attainable is 0. That point casts a distance, which we call d plus min, and that defines what the key generation footprint is for that particular satellite QKD system. Another thing to mention is that we process the overpass data as a single block and incorporate finite statistics to maintain a high degree of composable security. This is particularly useful when you have a large number of links of satellites and OGS, because you don't then have to partition and keep track of each of the links until there is enough data for key generation. So now we come on to what the secret key length is. So the finite key length was first derived by Charles Lin in his PRA paper with co-authors in 2014. So that is for 3 intensities, mu1, mu2, mu3, where mu3 we take to be the vacuum and their probabilities, we have a finite block secret key length given in this box. Now the finite secret key length is determined from finite sample data block sizes. Specifically, the key difference between an operation over an optical fiber is that in satellite QKD, you only have access to a finite number of data. So we can't assume an asymptotic number of transmitted information. As a result, the trade-off between the portion of signals that are used for key generation and parameter estimation really becomes important, with statistical uncertainties playing a big role. And the way those uncertainties are handled are through what we call correction terms. So here is our block size, n, and we have delta, which captures a correction term which accounts for the finite statistics. Now, in early treatments, the correction terms were determined from the standard deviation of observed statistics, but recent security analysis have improved, and they use smooth min entropies to provide a tighter bound. So there are a variety of ways you can model delta. So instead of using the Hoeffding inequality, we use the multiplicative Chernoff bounds to define what these correction terms are. And that's really because we get a higher optimized secret key length. So for more details on the multiplicative Chernoff bounds, I've included a link so you can see more information. So just breaking down the secret key length, what we have is the photon yield, which is SX1. Typically, we don't use single photon sources, we use B-coherent pulses, but because there's a possibility of multi-photon events, which are susceptible to photon number splitting attacks. We have this bracket 1 minus the entropy of the phase error rate, which captures the multiphoton events. We then have the vacuum yield, which is SX0. Now, since the vacuum events are uncorrelated, we need to post-process the raw key that we have, and that leads us to the error correction stage, which is shown in green, and that depends on the error syndrome M. And just to see how the secret key length really plays, rather how the finite block size effects play into the secret key length, we show an expression for the photon yield, and similarly for the vacuum yield and the error correction. So not much to take other than just to highlight that the secret key length is can be a lengthy expression that depends on the finite block lengths and the protocol parameters. And just to mention in passing, the error correction stage can have a simpler expression where we just take the first terms of the block size times the entropy of the quantum bit error rate, and where we multiply it by an error correction efficiency, so something that's greater than 1, which we usually take to be 1.16. But here we take a expression that was developed by Thomas Michael and colleagues in 2017, and this generates an improved optimized secret key length. So we optimize the secret key length of the protocol parameters, that's mu j and pj, and the basis encoding probabilities, but there is an additional optimization parameter, and that's the transmission time window. So just to develop some intuition as to why that is, it's simply because our transmission is across the atmosphere, which is a highly variable channel. So this means the expected observed statistics vary significantly, and data from low elevations has small count rate and a high quantum bit error rate. So this indicates what we can do is optimize the secret key length by essentially truncating the poorer quality data at low elevations. And this is an important trade-off in the block size. So if we have a look at a particular satellite overpass, then we impose a minimum elevation theta min, which accounts for local horizon effects near the OGS. And we take theta min in this work to be 10 degrees. And as we were referring to previously, the data that is transmitted by the satellite to OGS in the red regions has not only low count statistics, but low QBA. So we truncate those data signals and only consider what is shown in blue. So that's around t equals 0, and we consider a delta t time window about that point. And just to see that effect more clearly, we optimize the secret key length by taking specific values for our time window. And what we see generally is that for low system link efficiency, so for example, 27 or 33 dB, it is better to construct keys using the greatest amount of data, so the max delta t, which in this case would correspond to when the satellite is at 10 degrees in its overpass. For higher system link efficiencies, then it's better to use data around zenith. So what we see is for 40 dB, which is more typical of what a SAT-QKD system will operate at, taking a large DT will in fact reduce the secret key length. So we want to be able to optimize that to really get the peak of the red curve. And this really is due to the better average quantum bit error rate over the transmission path, which counters both the smaller raw key length and larger statistical uncertainties. So we've established our optimization program, which is the objective function is just the secret key length, and we maximize it over our protocol parameters, which is the basis encoding, the source intensities and their probabilities, and the time window. For full details on this optimization and its insights, have a look at our paper on arXiv, which goes into a lot more detail. But we've recently implemented the optimization program, which we call SAT-QMA, or Satellite Quantum Modeling and Analysis Software. And this is made available on GitHub to download. We've made it modular so that we can easily extend the applicability of SAT-QMA to treat different SAT-QKD systems, be it protocols or better treatment of the atmosphere effects. And this is something that we're currently working on, specifically CVQKD. And it provides a very general toolkit to model a wide variety of SAT-QKD systems that it's going to be useful for upcoming satellite QKD missions. And as I said, it's available to download on GitHub on the URL shown at the bottom of the slide. So in terms of applications, what we want to do now is use our optimized secret key length to see if we can inform experimental design of satellite missions. So the first thing we do is we revisit the two categorizations of losses and see how the secret key length varies with extraneous count probabilities and the intrinsic QBA. So starting first with the extraneous count probability, if you increase PEC, you effectively increase the vacuum yield. However, it leads to a worse phase error rate and error correction. So the net effect will, despite the increase in the vacuum yield, it will be a reduction in the achievable secret key length, which we see in the plot here. So the solid lines correspond to a single overpass, dashed lines correspond to two overpasses, and the dotted lines correspond to the asymptotic case. What we see is that at high PEC, and depending on what system link efficiency you were operating at, we get zero secret key length due to the excessive QBA. If we also have a look at the intrinsic QBA, what we see is that increasing or decreasing the intrinsic QBA affects the observed count rates. However, what we see is that the secret key length is more robust to changes in the intrinsic QBA. So this would suggest that satellite QKD missions should focus on decreasing PEC. So that would be background light and detectors. This is more clearly seen if we look at the variation of the secret key length with both the PEC and intrinsic QBA. And what we can see is that the secret key length varies significantly in the direction of PEC, with zero secret key length attainable irrespective of the intrinsic QBA at high extraneous count probabilities. So this indicates more clearly that satellite missions should focus on improving background light suppression and detected dark counts over source fidelities and satellite alignment, and also extending the transmission overpass to closer to the horizon. What we can also do is evaluate the expected annual secret key length. So here we plot the secret key length with different satellite trajectories that are at maximum elevation points. And from this, we can calculate the area under this secret key length and ground track offset figure and determine the annual secret key length for an OGS at a particular longitudinal latitude point. And this table summarizes the attainable secret key length at 55.9 north, which corresponds to the point of Glasgow. And what we see is that at 40 dB, we get 2.8 megabits of secret finite key. So this is quite small. It can be improved, and one way to do that is to increase the accessible data that we have. And that can be achieved by using multiple overpass data. So here we focus on three systems. That is a specific configuration of the system link efficiency, the extraneous count probability, and our intrinsic QBA. We focus on these systems that generate zero secret key length for a single overpass. And what we illustrate is the pass normalized secret key per number of overpasses. And what we see is that for increasing number of passes, we get an increasing secret key length. And this really comes down to increased data block sizes, which drives down the statistical uncertainties from increased sample size. And a general remark is that the secret key length for M overpasses is greater than or equal to M times that which is attainable from a single overpass. For satellite missions that do rely on multiple overpasses to generate a final key, it is important to realize a particular security vulnerability that comes with greater latency. That is the time you have to wait to accumulate data to distill a non-zero secret key. Finally, what we have a look at is two protocols. That is the efficient BB84 and the non-efficient or asymmetric BB84 and symmetric BB84. So the only difference between these two is how the basis probability encoding is handled. Now, it's already known in the asymptotic regime, the efficient BB84 performs better than standard BB84. And we show that this same thing holds in the finite key regime. Specifically in this plot, for a particular system link efficiency, for example, 40 dB, we show in the solid line the efficient BB84 performance and in dashed the standard BB84 performance. And what we see is that asymmetric BB84 delivers more finite key. It improves the operational key footprint of a satellite QKD system. And in this particular case of 37 and 40 dB, we see an improvement of 3 dB gives a factor of 7.6 improvement in the annual key volume, which is a significant amount. And this improvement really comes down to the better sifting ratio and longer raw key length and better handling of parameter estimation in efficient BB84. So as a very quick summary, we've introduced a general numerical toolkit to benchmark system performance for SAT-QKD systems. We come up with specific insights, which is that SAT-QKD systems and upcoming missions should really prioritize background light suppression over higher intrinsic quantum signal visibilities or extending the transmission to closer to the horizon. Efficient BB84 provides a larger operational footprint than conventional BB84, and secret key extraction can be improved by using data from multiple overpasses. As future work, there are a lot of avenues of interesting work that we can work on, and one of those is a more comprehensive constraint to our optimization program, which reflects additional restrictions on our satellite QKD operation. And the second is to incorporate orbital modeling of constellations with associated cost performance trade-off studies. And so these are stuff that we are actively looking at, and also extending the applicability of SAT-QMA to alternative protocols such as CV-QKD. Thank you very much for your attention. And at this point, I'm very happy to take any questions that you may have.